Hello. Hello, everyone.
It is honor and privilege to welcome you all for this faculty development program on opportunity and challenges in modern power system day 4 morning session organized by Department of Electrical Engineering, Rajki Engineering College, Kannauj. Today we have with us distinguished expert Dr. Padmini Singh. She has extensive experience
in progress.
research and development. She earned his BTech degree from AKTU with honors and PhD in electrical engineering from IIT Kanpur. Currently, she is working as an assistant professor in the Department of Electrical Engineering, IIT Jammu. Prior to this, she was uh, in academic position as an assistant professor at VNIT Nagpur and IIIT Sri City and MIT University Noida. She has engaged in outgoing project grant from DRDO, ISRO, and various other agencies. She has received multiple awards and recognition, including the Best Paper Award at IRIA 2021. She has organized national conferences and cultural programs, actively involved in various academic and administrative roles at IIT Jammu, serving as a program advisor for BTech Electrical faculty onboarding in charge. She is also member of Digital Twin Design Program, Aesthetic Department, and Development of Basic Facilities, contributing to institutional growth and community engagement. Her research focus on event triggering, sliding mode control, fractional order control, cyber physical system, multi-agent control, and renewable energy system. She has various membership like IEEE, IEEE, CCS, TRS, and other various agencies. She will take a session on topic maximum power point tracking using optimal control strategy in solar power companion inverters. I encourage all the participants to actively engage and ask questions after the session. So without further delay, let us welcome Dr. Padmini Singh from IIT Jammu to begin this session. Ma'am, please proceed.
Thank you, Dr. Vijay, for such a introduction, nice introduction. Although I am not, you have given such a very elaborated introduction. So thank you for that. So I welcome you all for this seminar on maximum power point tracking using optimal control strategy in solar panel companion inverter. Basically, I am a control researcher. Whatever the research I have done based on the control things. And as some of you may be aware that there are opportunities for control engineers to apply their control in any engineering field. So that is our task. And why control is required? Because there is always some lacuna in all the systems we have, because we want our system to perform as we every system. You take any system of power electronics, power system, chemical engineering, mechanical engineering. What you want from a system? You want that your system should perform as you want, what is the desired. So In this talk, I will give you a brief introduction about the how renewable energy resource uh, in renewable energy resource like solar, how you will use the control algorithm in that. And for that, I have chosen the optimal control strategy because most of you have heard about the optimal control. We all want that our system should behave optimally, though it is not a very good controller in all the sense, but controller task is to achieve the desired. That is the goal of the controller. So any controller you can apply in any system. So the today's topic is maximum power point tracking using optimal control strategy in solar panel companion inverters. So three engineering is included in this. Using maximum power point tracking, some power system logic is used, network system logic is used, then optimal control strategy, some control logic is used, solar panel companion inverter, solar renewable energy resource with your power electronic device inverter. So this is the presentation overview. First, we will discuss about the MPPT basics. What is maximum power point tracking? Then types of inverters used for solar panels. Then we will discuss brief about the optimal control strategy and LQR theory. This is a part of optimal control. This is the basic starting point of the optimal control. Optimal control can be divided into a non-linear control strategy and a linear control strategy. So LQR is basically associated with the linear control theory. And then some equations related to our model, then simulation case studies and our MPPT performance, then conclusion and how you can uh, integrate that work with your future work. So first, what is the need of MPPT? Why we will go for maximum power point tracking? So what is maximum power point tracking? So we all know that in a highly interconnected power system, from the starting to the end side, from the starting we have generator, then we have transmission line, then we have our load side. Load can be consumer load, domestic load, any type of load. So from generating to distribution side, our some reactance or resistance drops are there, which we don't have the control over that. We don't have the control over that from the starting to the end side because of the windings of the huge complex power system. We don't have the control over that. So that is the inherent quality of your generating side, transmission side, and the load side. So how you will, in that case, how you will extract the maximum power? So we all have heard about the economic load dispatch, that if our incremental cost of the generating stations are same, then we should distribute that power to the load side in that manner. But what will happen when we have the losses which cannot be unavoidable? हम avoid नहीं कर सकते हैं the power which is the losses which are occurring in the transmission system. So what you will do for that? Then you will go for the penalty factor which is associated with that. So incremental cost and penalty factor should be some. In that case, it will give you the optimal solution. So we always go for the optimal solution for load dispatch also. So in power system, distribution of the power should also be optimal in nature. Our losses should also be optimal in nature. But whatever is in our hand, that we can control. Whichever is not in our hand, we cannot control that. So what is the strategy? So how to extract the maximum power? So we all have studied that maximum power transfer theorem in the our BTech first year or second year. So what is that? So in maximum power transfer theorem, if it states that if our internal load is equals to the external load, in that case, whatever the power should be transferred to the load side, is maximum. So how we can apply that in the real world problem? How you can apply the maximum power on the load side by applying that theorem? This is simply MPPT. This MPPT is used for, you can use it for solar power, you can use for your normal conventional power plants, you can use for other renewable energy resources. So this we have used that MPPT concept in the solar also, same way. So what it states, how you can practically apply the maximum power transfer to the load side when your internal resistance is equals to the external resistance. So external resistance is in your hand, internal is in not in your hand. What is happening in the machine, you don't know. Once it is designed, you don't have the control over it. For the transmission line, once it is designed, you don't have the control over it. Only you can analyze what types of losses are incurring in the lines, in the machine, on the load side. So load side, you have the control. You have the control over the load side. So what you will do? First, you figure out the characteristics of your internal resistance or internal impedance behavior. On that behavior, you try to match your load side resistance should match the internal resistance. So when you will match the two, in that case, the power transferred by the any system will be, any resources will be the maximum. So that is the MPPT. That is why MPPT is so common in all the energy conversion systems, whether it is your renewable energy, whether it will be your conventional power energy resources, or in your power electronics devices, in your analog devices, in your electronic devices. We want to consume the maximum power, and we know that maximum power is not transferred at the maximum current or the maximum voltage. The only condition is when your load will matches to your source, and since source is not in your hand, you have to make your load match with the source. So first you have to monitor how the source is varying. Only you can monitor the source impedance, source losses which are occurring, then you can adjust your load resistance impedances. Either you have to insert more load, or either you have to remove the loads to match the maximum power should be transferred to the load. So that is the basic concept of maximum power transfer theorem. So same in solar panel, solar companion panels, what you will do, you will plot the VI characteristics of your solar panels, and based on that you will identify the point where the maximum power can be transferred to the load side. So that is the need for MPPT, because we know that the solar energy get transferred from the either we can store it in the DC format, a battery storage, or we can transmit it using by converting it through the inverters on the grid. So why we use inverter? Why we use inverters? We cannot, because all the domestic appliances and the consumer side we use AC. So we need to convert that DC which we are getting or which we are storing in from the energy which we are receiving from the solar, and we can, through the solar panel, we can store it in the form of battery. So you have to convert, because we are consuming the AC, so we have to convert it with some inverters. So that is why solar inverters are needed to convert DC to AC power, and when and that power should be sufficient to utilized by the domestic or commercial users. If that power is not sufficient, then we have to, it will be useless, or it will be most, if the losses will be more, then it will not be at the consumable side, it will not be useful. So we have to take care that whatever the power we are receiving, it should have such efficiency, or such it should be sufficient enough to be utilized at the consumer side. So that is why centralized architecture of panel should be there so that it should combine all the solar power together, and then it should be converted into the AC side to ensure the maximum efficiency. Efficiency maximum will be ensured by the MPPT only, conversion of DC to AC by the inverters, and the rating of that inverter depends on the consumer requirements. So basic MPPT techniques involve voltage loop control, current loop control, and your incremental conductance method, perturb observe method. So these are the methods in which, because if you want to control the load through these techniques, because in we all know that in the inverter there are lots of harmonics are there. So we have to compensate that harmonics also. Power system drawback is it has lots of losses. So we can we can compensate with power electronic devices, but power electronic devices again has lots of harmonics in it, because once you include the power electronics switches in your power system, it will insert the harmonics in it, third harmonics, fifth harmonics, all the odd harmonics it will include. So it will distort the shape, the pure sinusoidal shape which you want, you will not get. So that thing you have to take care that to how to reduce the harmonics as well as reduce the losses as well as get the maximum power to be transferred at the load side. So all these things you have, this is the your desired values, but how you will achieve these desired values? Definitely, we can use by some control strategy. It may be PID controller. We all know, we have all have studied in our BTech. It may be PID controller. It may be PIP controller. So every controller has some its own features, its advantages, disadvantages. So without the controller, everything desired will not be achievable. Something you can get by changing the features at the transmission side, at the generation side, at the load end side. But if you want to achieve the desired at all the points, then you have to put the controllers based on their merits and based on your requirements. So that we will discuss here that this is the decentralized conversion of solar DC power to AC power. This is the block diagram. So here you can see the panels written in CEC, see the CCC, and this is the solar panels from where the solar energy falls on the panels, and it is then the solar energy can be stored in the form of a DC value. And you know that this orientation is also fixed. Means my orientation is fixed, so my internal resistance, whatever the internal resistance offered by these panels, are also fixed. So in one way you can modify the structure, like we can mechanically make the solar PV arrangement such that with the variation in the daytime, with the with the sun position, we can vary the mechanically the position of the solar PV panels. We can make such arrangement so that the maximum power of the solar energy should fall on the PV panels throughout the day. So if we can make such arrangement mechanically, so this can be done mechanically. There is nothing to do with the in the sense of electrical, in the sense of signal. Here we can use the mechanical arrangement such that the maximum energy should fall on the panels. So in that case, the maximum your maximum power point should be achieved throughout the day. So one thing you can do like that, and that mechanical arrangement also have some control loop like that. Wherever the sun is moving, your PV panel face should be rotated in such a manner that it should face the sun. So through some control logic, it can be anything, PID. So what basically controller do, it tries to close loop controller. Open loop, we all know we will give the desired and we will get the desired with some error. Desired we give and act, we want our system to respond like that, but it always have some error. But when we give a closed loop signal, closed loop uh, we some feedback through the closed loop signal to our main system, then our system is forced to behave as the desired, and it tries to catches the desired to, and the error in that case, steady state error in that case, will be minimized. So if we are able to send the feedback of that mechanical arrangement, okay, that PV panel should face the sun maximum time. So in that case, the solar energy which is falling on the PV panel will be maximum, radiance energy will be maximum. In that case also, we are able to store the individually maximum DC storage would be possible. So you can see that V1, V2, V4, all these things, single inverters are used, and we are getting V1, V2, V4. And why we have used MOSFET based PWM inverter? Because MOSFET based inverter require only a certain threshold voltage at their gate in order to switch high voltage and current with high frequencies and low power losses. So that is why, and MOSFET is also a fully controlled switch. So that is always recommendable for the inverters. And why PWM inverter is used? What is the advantage of PWM inverter? Why we have not used simple inverter? See, at the C block, first we have solar panels, then whatever the energy we are getting at the C block. See, and that energy is in the form of DC. That is the DC energy. And through the inverter, we are transforming my DC energy, DC voltage to my AC voltage. So that is the inverter is doing. And why MOSFET? Because it requires less voltage at the gate to switch on. Okay, so my efficiency, because gate signal, we are not, gate is just like a, for switching on the inverter. Gate signal, whatever the gate signal we require for just switching on the inverter, just we want to convert whatever the DC we are getting from the solar PV panel to convert it into AC. The maximum energy we will get at the DC, the maximum amplitude of V1 we will get at each inverter. So likewise, in you can see in series V1, V2 and V4 are connected. So like this. So these are a sample of a micro inverter plus string inverter plus central inverter system. So basically solar inverter systems are of three types: central inverter systems, central inverter, string inverter, micro inverter. So all these three has some merits all and some demerits. So central inverters has high efficiency because in central inverter you connect lots of series with parallel combination all together, and its efficiency is also very high. And you can get a very high voltage at one, and the conversion side, like here we are adding for V0 is my output, V1 plus V2 up to V4. So we are serially adding it. In place of that V0 we will combinedly get a high magnitude voltage. But what is the drawback of central inverter system? That loss of a single inverter leads to the loss of the entire or a large part of the power generation. So once the fault will occur, fault can occur at any point. Because of the excess heating also fault will occur. So because of fault, if fault occurs in central panel at any time, then entire or in large part of the power generation will be affected. So we are not able to identify where is the power, at which panel the power is, that the fault is occurring. So that is why central inverter system is not recommendable for very high, means if you are very assured that okay, my inverter is not going to fail at such a high cost, and if you are fixing your short circuit MVA rating very high, for that again you have to put the your protection devices in with the your power electronic devices for the safety purposes. So our ultimate goal also to achieve the maximum power with less capital cost. If my capital cost is very high, then what is the advantage of achieving such a output at high cost? Why we go for the renewable energy system? We go for the renewable energy system because it is in India, solar energy is free of cost. Nobody is going to charge you for the solar energy. Just for all the design methodology, you have to pay. So that is why government is also emphasizing on putting the solar panel, your solar power plants, and they are giving lots of subsidies for installing that solar power plants. So that is why here we have used our solar panel companion inverters in this, where it has the combined effect of central inverter system, string inverter system, and micro inverter systems. So in micro inverter system, the arrangement is like that: only single inverter output will be there, and you can then amplify those signal with some DC AC to AC cycloconverter like that. So again, you have to make the circuit will be complex, means you are taking V1 V2 V up to V1 V3 Vn or V4, whatever the amount of signal you require, and then again you have to put some power electronic devices, and the more the number of power electronic devices you are going to insert in the circuit, the more total harmonic distortion will be there. So the shape which you want, the pure AC, is going to be distorted. So that thing you also have to keep in mind, and you want that to be also to be addressed. So what is the alternative for that? You cannot go for micro inverter, you cannot go for a central inverter system, you cannot go for a string inverter system. So what is the other alternative? So other alternative is to take the advantage of all the things, and also use the less number of power electronic devices to reduce the harmonic distortion. So this is the technique we have used, that we have serially connected each inverter output through that distribution grid side. You can say that that S1, S3, that DC input we are giving to this, and through this inverter based, this is my MOSFET based PWM inverter, AC output we are getting. And this AC output we are combining V0 as V1 plus V2 up to V4, a big size, big amplitude, large amplitude size AC signal we are getting, and we can send it to my load side. So this is the advantage of using the solar panel companion inverter. So, and one more challenge is that is the shading effect. What is the shading effect? Like you can see here, we have solar PV panels. If we mechanically fix its orientation, then maximum power cannot be, means maximum power in the sense, with the change in the position of the sun, the power which you are extracting or falling on the PV panels throughout the day, it will not be maximum. In the daytime, in the noon time, it will be maximum. In the morning, if the orientation phase of the PV panel is towards the sunrise, then it will be maximum in the morning side. If it is straight, it will be maximum at the noon side. If it is phased towards the west side, it will, in the evening it will be maximum. So that is called the shadowing effect, that throughout the day you will not get the maximum power to be fall on the your solar PV panels. So that is called the shading effect, and you cannot, because of that the efficiency is reduced. Efficiency means that my throughout the day my power is fixed, whatever I am getting is fixed. But if we want to vary that, mechanically we have to change its orientation to reduce the shading effect. So one thing we can do, one controller we can fix for the mechanical side, one controller we can fix for controlling the PWM width of the, you can see that my V naught is the combination of V1 plus V2 plus V3 plus V4. Here 4 inverter we have used. So if you can vary the, you are able to vary the width of your inverter. What is happening with the fixed inverter where we don't use simple inverter? Your width are fixed. You are not able to control its width. So suppose if my load is changing and I want to change the width of or amplitude of my signal, then how I can get the varying control signal. So PWM technique for the power electronic devices is the efficient technique, so that by varying the width of the signal, your output your output signal, that amplitude will be changed. So it could be a single pulse PWM inverter, it could be a 3 pulse, it could be a 5 pulse inverter we can use. So by varying the width of your signal, your amplitude will change, and as per your requirement desired value, you can modify the signal. So here two controllers we have studied. One is at the by controlling the PWM signal, that also requires your control logic. And for mechanical orientation of your PV panel, there also we require our control logic. So how we will go for the control logic? So why controller is necessary, we have discussed. So here we have used the optimal control strategy. So what is optimal control? So we all have studied, whether we are a control engineer or not, maxima or minima, that is also called economic or optimal solution. So same we have a concept of optimal control in a control system. So what control system will do? It tries to optimize the behavior as per the requirement. So optimize the PWM signal for solar panel companions. Optimize, if you will use at the mechanical side, optimize the orientation of your PV panels. So in this work only we have used the optimal controller for optimizing the PWM signal. You can also extend this work by using optimal control strategy at the mechanical side also. So, and linear control theory is a part of our optimal control, LQR, linear quadratic regulator. Its name tells that it is applicable for linear system. So in control system, we categorize all the systems into category. First is linear system, other is non-linear system. Basically, whatever the system in real time are available, we study are of non-linear nature. As most of you belongs to power system, you in your research paper you will find that you have lot of non-linearities in your power systems equations, state spaces equations you have to solve. Why we go for state space equations? Because state space exhibit the behavior of your systems. All the states which you denote with the parameters x1, x2, x3, x4 up to n dimensional generalized theory. We use that in this vector is in n vector space, n dimensional states exhibit. But if it is a two-dimensional, it requires two states. Three-dimensional for mechanical system, three states. Power systems, In power system, you need to control voltage, current, frequency. These are the three parameters you need to control. But if it has some noise, if it has some disturbance, you need to eliminate that also. So your controller should be robust enough to eliminate the noise and disturbances also. So all these things you have to take care. So first thing, you have to formulate the state space equation for your whatever the system you have. So most of the system you have seen that you non-linear system you have converted it into the linear system. So what are the properties of linear system? So in classical control, we have studied whatever the root locus, Raut-Hurwitz criteria, Bode plot, Nyquist plot, it is associated with the linear system and very less order systems, 2 order, 3 order. Beyond that, you have to go for state space. Why state space? Because n number of states you can include, and practically we have non-linear systems in nature. We can linearize any system towards its equilibrium point into a linear system. Then you can easily apply the linear control theory for that systems. So that is why linear control theory is important, because you can linearize any non-linear system to a linear system, and it is dominated by its 2-3 root. So you can easily transform your state space equation consisting of 2 to 3 states. Like that, you can reduce your state space equations. So with the help of state space equation, you are able to identify, okay, this is my system. These are the states. States could be a voltage, current. In your power system, in robotic system, it could be a position, it could be a velocity. And as the complexity of the system increases, is states, number of states also increases. So you can apply any linear techniques, any non-linear techniques to control the behavior of your system. So here we have used the linear quadratic regulator for optimal control. This is one of the method of optimal control for linear systems. That is why it is called linear quadratic regulator. In optimal control, there are so many types of techniques. Constraint minimization, where you put some constraint on your system behavior. Okay, my system should behave like this, so this should be the constraint. Under this constraint, my system need to behave. So under that, what is my optimal control strategy? So that for optimal control, first you need to fix your cost function, what you want to optimize. So in the equation 2, you can see that we have taken some cost function. So because based on the cost function, you need to optimize something that, and you need state space. So equation number 1 shows the state space equation of my system, where ID and IQ are the direct axis current and quadrature axis current, and VID and VIQ are the direct axis voltage and quadrature axis voltage, which is depicted in this figure. You can see that figure 1 is this figure here. This is this figure entirely. This is figure 1. Okay. And now this figure 1 is controlled. Whatever the mechanical and your power electronics converters are integrated, and it is controlled by some optimal LQR based current control loop. So here the reference and the direct and the quadrature voltage difference are generated by my direct current and my quadrature current, where DQ variables are we are getting from the current transformer side, and when it is 90-degree phase shift, alpha beta variables quadrature axis current we are getting by shifting the 90-degree phase shift. So we will get IDIQ, like same we will get VQ, VD, and from these 4 variables IDIQ, VD, VQ, we will able to get my desired voltage on the direct axis, on the quadrature axis, and the this reference current we have to give. So we are generating the desired voltage of the direct axis and the quadrature axis based on my direct current and my quadrature current, my actual, these are ID, IQ, these are the actual values, these are the actual values, and these are the reference values. VD, REF, VQ, REF, ID, REF, IQ, REF, these are the reference values, because in control system we have to give some reference values that my system should follow the reference value, and that reference value and actual values difference is the error which we need to put in our controller. That error should be mitigated by the control action. That control action can be PID, that can be sliding mode, that can be anything. So whatever the error we are getting, we need to mitigate it using some type of control technique, and that control technique can be anything. So using that control signal, we will control our pulse width of my inverter signal. Okay, this is the amount, this is the voltage signal we want. So now you expand the width, now you shrink your width. So on that basis, the signal width can be controlled that in real time. So some signal you have to send. So this is the state space equation, because we need to control ID, IQ, VQ, VD. So this is my state space equation, depends on these 4 parameters you can see. So my input is VID, VIQ, and I need to control ID, IQ. Here you can see. So ID, IQ, this is my state space. This is a linear state space we have formed. This is the simplified version, a linear, because we want to apply a linear control logic in that. For linear system, you can apply a linear controller also and non-linear controller also. But for non-linear system, you have only left with non-linear controller. So only that choice you are left. Here we have linear system, and we are also applying a linear LQR regulator for that. So R, I are fixed. ID, IQ are variable. ID dot, it is written L ID dot, and when you will take L at that side, it will become ID dot is equals to minus RI by LID plus VID by L. So VID is my control signal, VID, VIQ. Through VID and VIQ, I am trying to control my ID and IQ, and ultimately in a closed loop, all the parameters will be controlled by this VID and VIQ. So what would be my value of VID and VIQ? Okay, so here we have, for designing a LQ or controller, we need to first define my optimal cost function. So this is a generic form of optimal cost function for designing the LQR regulator. This is the generic form. For non-linear controller, any optimal cost function you can take. So there are varieties of methods for that also. Any optimal cost function depending on your requirement. So here xt, x is my state, and states are my id, iq, and ut is also a vector 2 cross 1 vector. So vid and viq are my ut. R is different from this ri. This R is associated, this matrix is associated with ut. This matrix Q is a weight matrix. Q and R are called the weight matrix. So what you want? You want Q and R, you need to design. R, it is also in our hand because optimal cost function generic structure is known to us, but we need to give the weightage to the Q and R matrix. So what is Q matrix? What weightage should we give to Q matrix? What weightage should we give to R matrix? Basically, what we want that my uh, tracking should be desired. Tracking means whatever we want, whatever the desired we want, my actual should follow that. But following that actual, the effort or the cost we should pay should be less. Everyone want that at less cost we should get the maximum output. So that is our requirement. That is our wish. That at minimum cost our output should be maximum. That is everyone wish. Either we want to purchase something, we want that at less cost we should get the maximum thing. So that is the human nature. So that is also required for the control system also. We want the minimum control effort, that we don't want to put maximum control effort, because otherwise if you will put maximum effort for achieving for simple things, that means you are going to pay for it, and that is not a goal of that should not be goal of a true control engineer. We don't want to put maximum effort for achieving the desired value. So my effort should be minimum. So that is why R matrix weightage will be given less. Q should be given more. If you will go and check for the LQR regulator problems, you will easily find out that Q matrix weightage will always be given at the higher priority than the compared to R matrix. So Q and R matrix are basically in this case a 2 cross 2 matrix, because we have a vector of 2 cross 1 size. So using this and this matrix, this state space equation 1, we can write it in this form: xt1 is equals to axt plus but plus wt. In this form we can write, this is a state space representation of equation 1. In simple generic form, axt plus but, a and b are matrices indices. So now we have to optimize this my state space equation based on my optimal cost. And so what should be my controller will look like? Ut, here we need to put my control action, and that ut based on LQR will be minus k naught xt. Xt is the state function, state vector. It is again state vector is of id and iq. This id and iq. Okay, and K naught is the gain matrix which you have designed, and K naught is R plus B transpose PB. R you have designed, P you have designed because whatever the weight you want to put on your control action, that you have designed. B is given to you based on the state space model, and P is the solution of the Riccati equation. This is my Riccati equation. So P is equals to Q. Q is the weight matrix. Again, you have designed. A is given to you. PA, when you will solve this, minus A transpose PB, R plus B transpose PB inverse, B transpose PA. When you will solve it, you will get a quadratic equation in the terms of P. And when you will solve some values, you will get, you can put both values, because quadratic equation you will get two solutions. Some at some values you will get the optimal solution, at some value you will not get the optimal solution. So the gain value k naught, where you will get the optimal solution, you can put that value in your controller gain k naught, and then you will see that the performance of your system will be improved. And here we have also considered the noise also, because some noise will be inherently present in the system, and to overcome that, controller action is always required. Although through the mathematics it is not seen that how it is overcoming the noise, but using that control action k naught, when you will, your k naught will be high enough to mitigate the effect of noise, then it will be eliminated, noise will be eliminated. But if the noise amplitude and the frequency is very high, then you have to go for some robust technique. In that case, these LQR techniques will not be applicable or will not give you the desired result what you want. So one of the robust technique for designing the controller is a sliding mode drug techniques, where I also worked a lot in the field of sliding mode controller. The basic advantage of sliding mode controller is that it eliminates the disturbance, but it has the chattering problem associated with it. And if for the power system, for mechanical system, the small chattering problems can be mitigated, but means can be ignored, not mitigated, can be ignored. Sliding mode has the drawback of that chattering. So it actuates the unwanted dynamics of the system. And if in power system, where in fractions of seconds your voltage and current magnitude can be triggered so high, can be triggered so low, so there is sliding mode. Conventional sliding mode is not good enough in real time practices. It is not good. That is why you will find in most of the industry problems, they are still they are using the PID controller, because the in PID controller, the I action of the controller, PID basically means for proportional, integral and derivative. So derivative action improves the transient behavior. Your transient behavior is uh, improved using D controller, but your transient behavior is improved. But in using integral action, your steady state error is mitigated. That is why still in most of the industry, all the power systems we use, you will find, most of you may be working in the industries, there you will find that still PID controller is using. So what it will do, it will simply just whatever the difference you are getting from the actual and the desired, you set your tuning parameters Kp, Ki and Kd based on the Ziegler-Nichols method, and it works very fine. People are not going for higher order controllers because it suddenly actuates whatever the problem. If it suddenly actuates, then how to control that? Although these controllers are on theory much better than PID controller. In PID controller, we don't have the stability analysis. In mathematically stability analysis, you will not find very convincing, but still it is using. And in other types of controllers, mathematical analysis are very rigorous, and it will give you a very confined research constrained optimizing area. Okay, on that basis you can design your controller, on that domain you can design, on that constraint you can design, but still people are using PID controller. So that is the for applicability wise in power system, it is not much you can say in use. Okay, so this is the story behind the LQR converter, because it is also safe. This simply works like a P controller. You can see a simple gain is there and states. It depends on my UT. UT is my control input. Simply a gain you need to design based on the LQR function, and based on that you are giving a signal back to your PWM converter. Okay, this width signal I want, and it is if this my PWM signal is sent to figure 1, and now it is whatever the signal we are getting here, that is sent to the grid this side. Okay, now you can utilize that depending on my requirement. So this is the overall how you can include your controller for controlling the PWM signal. Any type of signal, any type of controller you can use here, any type of static space equation you want, whatever you want to control. That is the beauty of a control system. What you want, you can design the state space like that. If you are not satisfied with the some controller performance, you can switch to other controller performance, and you can check, because this state space formation is also not fixed. And if you will go for a non-linear system, a non-linear state space equation, and you design, then you will find that it is performing better than my non-linear, than my linear system behavior. So anything you can do, you have the possibility of changing anything in this. From starting to the end side, you can, in the design side you can change, in the control side you can change. There are lots of possibility of including controller in power system, power electronics applications, because ultimately your goal is to get the desired value of voltage, frequency, and current. So it can be controlled by at any point, at the inverter side, at the starting source side, at the load side. So whatever maximum power point technique is using, that it is trying to match the, it is trying to control the internal signal behavior as per my output requirement. So it is trying to matching that point, and we have only the output. We don't have the what is happening in the input. Only we can control some signal in some manner. We can insert a control structure, a controller with my system, okay, that you should behave like that. So that we can do. So we can observe, we can measure our output, and based on that we can give the reference value. Okay, this is the reference value I want. So based on that reference value and actual value, we can go for the desired reference value, and that overall that thing we need to achieve. So this are the, we have used using LQR converter, and this is our result. Tracking performance of grid voltage when one solar panel has measurement noise, because how the noise are mitigated using LQR, it is shown here, that in the presence of noise, how my V grid and I grid is changing. You can see that it has harmonic sinusoidal shape. It has my voltage which we are getting here. It has, with solar panel companion, whatever the voltage we are getting, it has harmonics, because it is a combination of its odd harmonics and plus fundamental. So you want your fundamental to be more, so you can include filter in there also. You can apply a control logic in that. So there are on the various conditions how my signal is behaving. It is shown in the figure, and this is the figure for PV curve showing maximum power point tracking. You can see that at the maximum voltage we are not getting the maximum power. It is in between the maximum and the minimum, shift tilted towards the maximum, but not maximum we are achieving at the maximum voltage side. So this why we are getting this shape, because when in the case where my external resistance, external impedance is matched with the internal, in that case whatever the power we are getting is maximum, and that is our goal. So you can modify this curve also by inserting more and more controller on your system, but again the inserting more and more physical controller in your systems will somehow enhance the performance, but at a cost of more capital cost or more complex system you are making. But the desired, if your it always depends on the desired value, what you want to achieve. If you want to achieve maximum power, you can control the PWM signal, you can control the mechanical structure of your PV signal. But if you want to, your loss should be less, then in that case you have to control your losses should be less, then internal impedance should be less. So your transmission means small control signals you have to amplify at uh, whatever the signal you are from the sending to the receiving and you are getting, you have to amplify at some interval of time. So that thing also you have to keep in mind, that what should be your goal, what do you want to achieve. On that basis you need to deploy your controller on that place, because applying controller in all the places may be something you will get, but still it will again increase the complexity of the system. And once if the system, and if you increase the complexity of the system, again the reliability of the system will be less, because once it will fail, the error will be propagated. So that thing you have to keep in mind. So what is the future scope? That PV curve and MPPT. This illustrates the relationship between voltage and current. MPPT controller optimize power output, dynamically adjust operating point. So benefits of MPPT with optimal control, that higher energy you can extract, adaptability to changing conditions, improve solar energy. So what is adaptability? What is adaptability to changing conditions? So here you can see that whatever the cost function we have taken, it depends on the states and weight matrix Q, input U, and weight matrix R. So no constraint we have further put on our optimal cost function. It's a simple optimal cost function we have taken. So if you want to modify your controller, your LQR performance you want to modify, then you have to modify your cost function, or you have to put some constraint on that cost function. Like here it is written, the adaptability to changing condition means your cost function should not restrict to like this. It should have some more thing in it. So, but cost function, since you are controlling the states with some input, so cost function is not going to change. Only you can put along with the cost function some constraint on your cost function, that Q and R should be designed such that it should follow certain constraint. So that is called the adaptability dynamical conditions. That thing you can integrate with your optimal cost function. Okay, by finding Q and R and K naught, also that K naught should be adapt, should fit my some constraint which is compulsory for the your system performance. So some constraint you have to put in that. So this is the advantage of optimal control theory. You can, in any control theory, like unlike to PID you cannot modify as per your requirement. You cannot modify the PID controller further. But in optimal control theory, you can put more and more constraint. Your K naught will be changed. But in PID, once it is designed, only your gain can be changed based on your error. So whatever error you are getting, but here error as well as constraint, whatever your requirements are there. So you can put more and more constraint along with the cost function. On that basis, you can change your gain. So that is the beauty of optimal control system. Likewise, a sliding mode controller, there are 2-3 stages of designing sliding mode controller. First is your designing of sliding function, sliding surface. Then you can design your reaching law. Then in that, some reaching law are already existing, and some reaching law you can also frame based on your requirements. So the more parameters if you are including in your control law, you have the more flexibility of tuning the parameters. If you have more tuning parameters, then you can achieve the desired values. Because what if you have, like, if you have more controller parameters things in your hand, you can twist, you can play with that. But if you don't have any control parameters in your hand, how you can change, how you can uh, vary the things as per your requirements. So that is the advantage of other controllers over PID. But since PID is very simple, very less chance of PID to fail, that That is why still it is in the industry it is used. So this is the future scope, that non-uniform radiation conditions, like I have discussed in the starting, that non-uniform radiation conditions, because here we have assumed that my position is fixed. This position of my PV panels are fixed. Whatever the radiation is falling on the means my PV panels throughout the day, if you will measure, it is not going to change. Maximum means it has some shadowing effect. It depends on the weather condition. It depends on the solar position. So someday maybe you will get maximum at some point, at some instant of time. Maybe other day maximum you will get at some other instant of time. But if you will change the orientation of the panel as per the sun condition, you will throughout the day you will get the maximum signal, maximum efficiency. So that is also the future scope. You can go for that also. You can use different control techniques for modifying that. You can include more and more noise and disturbance like WT in it, because all the real-time systems are inherent with disturbance as noise. So you cannot simply take a simple state space equation excluding the noise and you can draw any controller and say that my controller is best. No, the more you will include the practical uh, disturbances, masked uncertainty and unmasked uncertainty in that, the more mm, it will be more practical. And one more thing, designing a linear controller, taking a linear system compared to non-linear system is like you are just not seeing the complex. You don't want to see the complexity of the system. You want to go for an easy solution, but easy solution is not a good solution. So easy solution is not a good solution. So try to take the non-linear system dynamics and draw and design a controller for that. Then you will see that although it is very hard to design a non-linear controller for non-linear system, that is why you will find in most of the power system papers we use to simplify the model, the states in the linear model. We used to simplify it, and it has maximum 2 states, 3 states, 4 states, not beyond that. But but your goal should be that your system should include all the parameters having non-linearities, and then you design the controller. It will be applicable, but for all types of systems. So if you simplify the system, that definitely means that in practically your controller is not going to work. That is definite. But if you will take a very complex system and design a complex controller for that, that is guaranteed that it will applicable in all types of systems. But once if you simplify the system and design a controller, then it is going to fail at some point. So better to take the non-linear system, or if you want to take a linear system, then want to convert your non-linear system into the linear one, that it will always preferable to consider those eigenvalues which are dominant. Like we have in our system, any system is governed by 2 or 3 major eigenvalues. The more yeah, I don't think you people have studied about the linear system theory. Linear system theory, we talk about the dominant eigenvalues. Eigenvalues, we all know that from the characteristic equation of your transfer function, you will get the eigenvalues of any system. But if you will observe the eigenvalues behavior, you will find that any system, whether it will be an order, 4 order, 5 order, any system, it will dominant by its basically two eigenvalues. That is why linear system theory is also still in use. Otherwise, most of the system are of non-linear nature. Why we still using linear system theory? Why we still go for that simplified linear state space equation and design linear controller for that? Because we assume that this is the dominant the character this linear system is having is dominant by its dominant by its eigenvalues, which characterizes the entire power system which we are talking about. So that is why you can linearize your nonlinear system through its equilibrium position and get the solution for that. It will work at some extent, but if it will be non-linear, that it will be better. So that's all from my side. So any questions you can ask?
Participant, if you have any question, please you can ask.
These are the faculties of different institutes.
Yes, yes.
Online they have joined or physically they have joined?
Approximately all have joined.
Okay, this FDP is online.
Thank you, Padmini ma'am, for your.
So I think no question is there. So you can mail me. You can take my email. If you have any question, you can take the email from Dr. Vijay and you can mail me regarding any queries. Thank you. Thank you all.
Okay, thank you.
So can I leave?
Yes, yes.
Okay.
Recording stopped.